Welcome to our discussion of multiplication and division of fractions. We're going to look at multiplying, dividing, simplifying complex fractions, and then solving application problems using formulas and basically using fractions. All right, multiplying fractions. Pretty straightforward. In fact, this should be the easiest operation you do with fractions because you don't have to worry about common denominators or any of that junk. When you multiply fractions, you simply multiply the tops and you multiply the bottoms. So in a general sense, if you have a over b times c over d, you get a times c, and on the bottom you get b times d. That's it, simple. 2/5 times 1/3, 2 times 1 is 2, 5 times 3 is 15. There's your answer, 2/15. All right, if you want to visualize it, why does it work this way? Well, 2/5 times 1/3 really means you're going to take 2/5 of 1/3, right? That's what multiplication means. So you can read multiplication as the word of. Now at the right-hand side, this first figure, you can see that 1/3 of it is shaded. Now, if we want to shade 2/5 of that 1/3, we have to cut everything into fifths, which you can see we have 5 columns, right? So these are all fifths. And 2/5 of the shaded region would be these two blocks here. And now if you count it all up, how many total blocks are there? Well, there's 5 times 3 is 15. 2 of them are shaded. So we end up getting 2/15 of the entire shape, right? We started with 1/3. We took 2/5 of that 1/3 piece, which gave us 2/15 of the entire shape. Right, so that's how fractions work. You're taking a fraction of a fraction, means you're getting an even smaller piece of the whole, as long as both of those fractions are actually proper fractions, right? Remember, a proper fraction means smaller than 1. Okay, so if a is a natural number, any natural number, and a natural number, remember, is an integer greater than 0. So natural numbers are like the counting numbers, 1, 2, 3, 4, 5, 6, 7, and so on and so forth. So if a is a natural number, then we know that 1 over a, which is called the reciprocal of that number, or the multiplicative inverse of that number. And what that means is it's the inverse of that number over multiplication. If you take the number a and multiply it by its inverse, the answer is the multiplicative identity. And the identity for multiplication is 1, right? Because 1 times anything is 1. That's why when we talk about just regular, an additive inverse, well, if we have a number a, then the additive inverse is negative a, because what's the identity element for addition, right? What can we add to anything and not change it? 0, right? Just like we can multiply anything by 1 and not change it, we can add 0 to anything and not change it. So the additive inverse of a is negative a, because a plus negative a gives us 0. But when we're doing multiplicative, right, when we're doing multiplication, the identity element is 1, because 1 times anything is still itself. So in order to get 1 from any number, we just multiply that number by its reciprocal, which is 1 over that number, right? So a times 1 over a gives us a over 1 times 1 over a, because we have to remember that any whole number can be written as a fraction divided by 1. And we multiply fractions. We just multiply tops and multiply bottoms. And we get a over a, which, of course, reduces to 1. So the product of any number and its multiplicative inverse is always 1. 1/8 times 8 is the same thing as 8 times 1/8 is equal to 1. 1/9 times 9 is equal to 1, 1/10 times 10 is equal to 1, and so on and so on and so forth. And it even works with negative numbers, right? Because -7, the reciprocal would be -1/7, and we do -7 times -1/7. The two negatives cancel, and we still get +1. Okay, when a factor is a mixed number, we want to first write the mixed number as an improper fraction and then multiply. So that's why before, in other videos, we learned how to switch from mixed numbers to improper fractions, because if we're going to work with mixed numbers, it's a lot easier to work with them as improper fractions. Now, when we're adding and subtracting, we can go ahead and leave them as a mixed number, and we can still do the math. But if we're multiplying and dividing, we have to convert them into improper fractions. And oftentimes, even when we're adding and subtracting, it makes it easier to turn them into improper fractions. So it's a good skill to practice, being able to go back and forth from a mixed number to an improper fraction. All right, before we get there, let's ask ourselves, is 2/3 a solution of this simple equation 3/4 x equals 1/2? Well, simply all you got to do is plug it in. 3/4 times 2/3, you do that math, you get 6/12, which of course reduces to 1/2. And 1/2 does in fact equal 1/2, so therefore it is a solution. Just remind ourselves that whenever we do this work, it's always a good idea to take our solution, plug it back into the original equation, and make sure it fits, make sure it works. We catch our mistakes that way. Okay, if we want to multiply these two numbers, you really can't do it easily. It can be done, but it's not easy to do it as mixed numbers. It's much, much easier and much simpler and much safer, less chances of mistakes, if we turn them into improper fractions. So we're going to turn 7.5 into 15/2. Now, if you don't remember how that's done, you basically think of 7 as 7/1, and then you have to do a common denominator, so you have to multiply top and bottom by 2, which gives you 14/2, and then 14 plus 1 gives you 15 times 2. The shortcut is take the bottom of the fraction, multiply it by the whole number, and add this. 2 times 7 is 14, 14 plus 1 is 15, 15/2. 5 times 4 is 20, 20 plus 2 is 22, 22/5. And now we can multiply these as normal. Now here's a trick, I shouldn't call it a trick, it's a technique that will help save you some time. Yes, you can just do 15 times 22, get a big old number, 2 times 5, get 10, and then have to worry about reducing that fraction. But it's a lot nicer if you reduce before you go. 15 is just 3 times 5. 22 is 2 times 11. When you write it out like that, and then the bottom is 2 times 5, we can see that the 2's cancel, the 5's cancel, and you're left with just 3 times 11/1. 33/1, the answer's 33. All right, now what about dividing fractions? Can we divide fractions in both directions, right? We saw that 2/5 of 1/3 is the same thing as 1/3 of 2/5. But what about division? Okay, the reciprocal of a fraction is just like the reciprocal of a number, right? The reciprocal of a is 1/a. Well, the reciprocal of a fraction is 1 over that fraction. But when you divide by a fraction, you're multiplying by its reciprocal, right? So you're doing division of division of division, and it flips around and around and around. And basically what happens is the reciprocal of 3/4 becomes 4/3. And the reciprocal of a over b is b over a. Because what do I multiply 3/4 by to get 1? Remember, that's what reciprocal is. It gives us the identity of 1. So 3/4 times what is going to give us 1? Well, it's got to be its reciprocal. 3 times 4 over 4 times 3 gives us 12/12, which is 1. All right, so all you got to do is flip your fractions to get your reciprocals. And we do that because that is what enables us to turn division into multiplication. We just saw how easy it is to multiply. Multiply tops, multiply bottoms, we're done. Well, 6 divided by 2 equals 3. 6 times the reciprocal of 2, which is 1/2, also equals 3. So we can see that when we're dividing by a number, it's the same thing as multiplying by its reciprocal. So if we have a fraction and we're dividing that by another fraction, we can make our lives easier and turn it into the first fraction times the reciprocal of the second fraction. So 2/5 divided by 3/4 is 2/5 times 4/3, which gives us 8/15. Now I asked the question earlier, right? We know that 2/5 times 4/3 is the exact same thing as 4/3 times 2/5. But what about 2/5 divided by 3/4? Is that the same thing as 3/4 divided by 2/5? Well, unfortunately, the answer is no, because 3/4, right, divided by 2/5 equals 3/4 times 5 halves, which equals 15/8. And you can see these two answers are actually, what are they? Reciprocals of each other. So division does not work in both directions, meaning A over B divided by C over D is not the same thing as C over D divided by A over B. Unfortunately, it doesn't work like multiplication. You end up getting the reciprocal. And yes, you always get the reciprocal. Okay. Remember that when we divide a fraction and a whole number, we first write the whole number as a fraction with a denominator of 1. It's the same thing we did when we multiplied. So if we're trying to figure out something like this, where we've got a simple x divided by y, where x is 3 and an 8 and y is 5. So now we have this ugly looking thing of 3 and an 8 divided by 5. We have to remember that 5 is the same thing as 5 over 1. We also have to turn 3 and an 8 into an improper fraction, right? 8 times 3 is 24. 24 plus 1 is 25. 25/8. Now we have something that we can manage, right? We have a fraction divided by a fraction. But we can turn that into multiplication by flipping that fraction, right? Getting its reciprocal. Now we get 25 on the top, right? 40 on the bottom. Or if you want to save yourself some time, you can factor out the top, because you notice that, 25 has a 5 in it. This is really 5 times 5 times 1 all over 8 times 5, and then you can cancel the two 5s, and your answer is just 5/8. Now, if you didn't do that, and instead you just did the multiplication, it would still reduce out the same way, right? If you didn't do this and you just did the math, you'd have 25 over 40, and then go, oh, hey, those are both divisible by 5. 25 divided by 5 is 5. 40 divided by 5 is 8. And you could do it by reducing, your final answer. But it's a lot easier if you can reduce as you go. All right, what about complex fractions? Well, a complex fraction just means fractions kind of within fractions. So here are some examples of a complex fraction. You see how you've got kind of the bigger fraction is this big piece divided by this big piece, and the main fraction bar is thicker and bigger and darker, right? So you can see that that kind of takes precedence, and we can see that this is really just something over something. This is basically of the form, I've got some stuff here, and it's being divided by some stuff here, right? Same thing here. Something being divided by something else, but that something else has a fraction within it, right? Here's one piece being divided by another piece. This is my main fraction bar here. And again, one thing divided by another thing. But those things, instead of just being simple numbers, are now junk. They've got all sorts of weird stuff in it. And so you have to clean it up. Now let's say we were looking at this first one. Isn't this easy? Because isn't something divided by something the same thing as something times its reciprocal? So couldn't we turn this into 3/4 times 8/7? And then we could do that math. So that tells us that if we have something in this form, in this first form, we're good to go. If we have one fraction over one fraction, we're fine. We can work with that. So that now becomes your goal. Anytime you've got a bunch of ugly junk, and you can't just get a number over a number, right? 4 over 3, 4/3, 5 over 7, 5/7, easy. If you can't do that, then see if you can get a fraction over a fraction, because then you can turn it into multiplication of its reciprocal. And that's going to be a technique. It's kind of another tool in your toolbox. So how about trying it with something a little bit more complicated, like this one. Well, we know that if we can get just one number over one number, whether it's a whole number or a fraction, it doesn't matter. So let's turn this bottom thing into one number and go 3 minus 1/2. Well, 3 is the same thing as 6 halves. 6 halves. 6 halves minus 1/2 gives us 5 halves. And now all of a sudden we have 4 divided by 5 halves. But we remember that division by a fraction is the same thing as multiplication by its reciprocal. We get 8/5, or we can write it as 1 3/5. Either one of those is fine. Right? How about this one? Well, again, we need one number over one number. So we have to combine these two. So we have to make this a common denominator and make it 6 over 10. So we get 9/10 plus 6/10, and that gives us 15/10, not 3/10. This is a big fat typo here. I think when I was creating this, I was thinking subtraction, 9/10 minus 6/10, and that's where that mistake came from. But as we see with the plus, 9/10 plus 6/10 should be 15 over 10, which of course, when you reduce, they're both divisible by 5, right? You get 3 halves. So this should really be 3 halves. Let's see if I made any other mistakes. Well, what's 1 1/4 as an improper fraction? Well, yep, that's 5/4, right? 4 times 1 is 4. 4 plus 1 is 5. 5/4. So that part's good. So now we've got 3 halves divided by 5/4, which is really 3 halves, right? Times 4/5, which is really, if you want to reduce, right? The 2 and the 4 will cancel out, but if they know that might complicate things for you. 3 times 4 is 12. 2 times 5 is 10, and then this reduces to 6/5, right? Or you could have reduced as you went, right? You could have taken the 2, would have canceled that and made that a 2, and then 3 times 2 is 6, and then 1 times 5 is 5. All right, how about an application problem that involves fractions, like the area of a triangle, which we know is 1/2 base times height. Well, what if we have something like this, a base of 6 and a height of 2? Easy, plug everything in. Area is 6. Well, what if we have a question like this? A 12-foot board is cut into pieces 2.5 feet long to use as bookshelves. What is the length of the remaining piece after, and how many shelves are possible? So basically, we're just trying to figure out, if we cut this thing up into this many pieces, what's going to be left over and how many shelves are we going to have? Any of you who've worked with wood, you know that this question is wrong because they're not taking into account the width of the saw blade. So for these types of questions, if you are a woodworker, just assume that the saw blade is 0, right? That if you took a 12-foot board and cut it exactly in half, you would have 2 exact 6-foot pieces, even though we know that we wouldn't, because there would be the width of the saw blade that would chew away the wood, and they would be a little bit less than 6, but this is math in a not real world sense, so to speak. Okay, so if we're trying to figure out how many 2.5 foot long shelves we could make, we have to take 12 and divide it by 2.5, which means we have to turn 12 into 12 over 1. We have to turn 2.5 into 5 halves, right? 2 times 2 is 4. 4 plus 1 is 5. 5 halves. Division becomes multiplication by the reciprocal. This gives us 24 over 5. 24 over 5 becomes 4 4/5 if we do the math, right? Because to go from an improper to a mixed, we just have to do the long division. 24 divided by 5, it goes in there 4 times. 4 times 5 is 20. 24 minus 20 is 4, and we get a remainder of 4/5. So 4 4/5, which means we have 4 shelves and then 4/5 left over. But what is that? Does that mean we have 4/5 of a foot left over? No, we have 4/5 of a shelf, right? We have 4 4/5 shelves. because each one of these was a shelf, right? If we're dividing by 2.5, we're dividing it up into shelves. How many shelves do we get? We get 4 4/5 shelves. So that 4/5 isn't 4/5 of a foot, it's 4/5 of a shelf. So we have to do 4/5 of the shelf length. 4/5 times 2.5, again, change that into 5/2, do the math, and we get a remaining piece of 2, right? 20 divided by 10. So that means we get 4 shelves, and then we get the last cut piece is 2 feet long. Yes, I know in the real world it's going to be a little bit less than 2 feet because of all the saw cuts, but that's the idea as far as the math is concerned. Okay.